this is a quick recap of the basic concepts that we talked about on Tuesday. So we started with mathematical preliminaries, and we said that since we want to study the deformation of an object, one of the first things that we have to do is to formalize the notion of space. So what do we mean when we talk about a space? What we exactly mean is basically this Euclidean pointer space. And we use letter E, the uppercase of script alphabet, to show that, and N is the dimension of the space. So N can be 2 or 3, for example, when we deal with two-dimensional or three-dimensional problems. What is En? En is a set of points in which we can actually apply the principles of Euclidean geometry. So what do we mean by that? For example, if we have 2 points in this space, point X and point Y, one of the properties is that you can pass a straight line through these 2 points. To write this mathematically, we can say that for every X and Y that belong to this Euclidean pointer space, basically we can pass a straight line. So this symbol here means for every or for all, and this other symbol here means belongs to. So when we have a line, one thing we can measure on that line is the distance between the 2 points. So we show this by d as a function of x and y. So we can take a measuring tape and measure the distance. If we want to formalize d is basically a function which maps 2 points in the Euclidean pointer space. That's the Cartesian product into a number, a scalar. So what are some properties of the distance? So something which is kind of obvious is that if we measure the distance between x and y, it's the same as measuring the distance between y and x. So the two arguments are interchangeable. Another somewhat obvious property is also that for every x and y that are in the Euclidean point space, the value of this distance is non-negative. So it's equal to greater than 0. So that kind of brings us to another property, that if you see a distance between 2 points is equal to 0, then you can immediately say that these are the same points. So this symbol here means if and only if. So when we have lines other than distance, the other parameter that we can measure is the angle between the two lines. So if we have 2 points x and y, and then we have another point z, we have 2 lines, and we can measure the angle between them. So this opens up discussions about other important concepts, which are parallel lines, perpendicular lines, and perpendicular projections. So when you have a point and basically you find the perpendicular projection of that point on a line, for example. Okay, so now from points, let's move to vectors. The concept of vector, as it is evidenced by the name, which comes from the Latin root vehere, which means transportation, it implies going from one location to the other, from one point to the other in the space. So we go from, let's say, point X to Y, and of course we use this symbol which has direction in it, and here X is the tail, Y is the head of the vector, and let's call this vector vector U. So we use the same notation for points and vectors, and this is somewhat convenient from many aspects, and the context tells us if we are talking about a point or a vector. For example, we can, using this notation, we can say that to get to the point Y, we have to go from point X through vector U. And similarly, vector U, we can write it as the subtraction of the 2 points. So this is not subtraction as you have seen in elementary algebra. This is an operation which is a point difference. So now that we have the vector, we want to look at some of the properties of the vector. So one important property is the magnitude of the vector, which is nothing else but the distance between tail and head. So and as we know, this is always non-negative. Another important property of the vector is that if, let's say, we have points x and y, and points y prime and x prime, and considering two vectors u and u prime, the question is, are u and u prime two different things? The answer is no. As long as they have the same magnitude, they are parallel, and they are pointing to the same direction in such a way that we can construct this parallelogram using these four vertices, we can confidently say that no, u and u prime are pretty much the same thing. So going to point y prime from x prime, we can write it through u or u prime, doesn't matter. This property facilitates another kind of operation which is associated with vectors, and that is the summation of vectors. So if we have vector u and vector v is somewhere else, we can move it parallel to itself and we can bring it such that its tail is at the head of the other vector, and this is the same vector, we are confident about that. And then the summation, as you have seen it before, would be the vector w, which goes from the tail of u to the head of v. Another important operation is multiplication by scalar. So if we have vector u we can multiply it by a scalar alpha. So alpha belongs to the set of real numbers, and alpha u is another vector. If alpha is positive, it points in the same direction as u, and if it is negative, it points to the opposite direction. And that follows that the magnitude, another property is that the magnitude of this scale vector would be the magnitude of the scalar times the magnitude of the vector. So this brings us to the definition of vector space. So we learned about point space. Vector space is a collection of vectors in the Euclidean space. So we write it like this. And this symbol here means such that and as I said, this represents vector space or sometimes it's called translation space. M is here also the dimension of V. Now, knowing that we want to go forward and to define linear combinations of vectors. When we learn what scalar product is, so if in the vector space we construct objects of the form alpha 1, v1, alpha 2, v2, alpha m, vm, where alpha 1, 2, alpha m, they belong to the set of real numbers, and the vi's belong to the vector space. Then this object, it's called linear combination of the n vectors by the scalar coefficients alpha 1 to alpha n. So that's where we stop. On Tuesday, linear combination has a lot of implications that we are going to see later today.